All right, we are going to take a look at calculating energy gained or released during phase and temperature changes. So you've been exploring heating curves, which show us the amount of energy or heat absorbed by a substance as it changes temperature or changes state of matter. So we can heat something up, or we can melt it or freeze it. We can heat or cool something, or boil or condense it, or heat gas. So different sections of this heating curve fall into different parts of the heating process and phase changes. If we were to take this curve, we could also reverse it and do what's called a cooling curve, or we can think about the direction. If heat is absorbed, we're going towards the right and we're adding energy, or we are going towards the left and energy is being released, okay, exothermic. So we're going to now look at calculating how much energy. So the heat gained or lost during a phase change, so changing between solid, liquid, and gas, which are in sections B and D of that graph, are done using the following equations. So this is how we calculate. Q equals moles times delta H of fusion, or Q equals moles times delta H of vaporization. So Q is going to represent the heat gained or lost by our substance. So it will be positive, we'll get a positive value if it's gained, or negative if it is lost, exothermic. Our moles are going to represent, of course, the moles of our chemical being heated or cooled. Our delta H of fusion is the enthalpy of fusion used for melting, which is positive, or freezing, which is negative. So we use the same value for both melting and freezing. We have to change the sign, though, depending on which one is occurring. So that is our responsibility. It will not be done for us. Same thing with heat of vaporization is the enthalpy of vaporization. It's used for boiling, which is positive, or condensing, which is negative. Again, we have to assign the correct sign to it. This equation is used when temperature is not changing during the phase changes only. So there's no temperature involved in these equations because the temperature is staying constant. It's those flat plateaus in the graph. The delta H values are given in the question. So we are going to be given these values, delta H, to actually calculate our values. Then we have a second equation. So last year in chemistry, we learned this equation, Q equals MC delta T. You might remember that. It was very early on in the last year. So Q represents, again, heat gained or lost, same Q. So they can be associated with each other. M is going to represent our mass in grams. C is going to represent the specific heat capacity or specific heat. Its units are joules per gram degrees Celsius. So I always remember this is the more complex unit, and that is what C represents. Okay, it has the complex units. And delta T represents the change in temperature in degrees Celsius, which is final minus initial temperature. Many students but get these things confused and mix these up. And sometimes that can cause issues depending on what you're trying to find. So Celsius is temperature, and specific heat is represented by just capital C, which is kind of weird. Okay. So this equation is used when temperature is changing. That's why we have delta T. So the chemical is being heated or cooled. All right, so we are changing temperature. This is used when we are in sections A, C, and E. Now, for this one, the heat gained or lost, Q is going to be negative or positive depending on the change in temperature. So if our temperature goes up, it'll be positive. We've gained energy. If the temperature drops and is negative, it'll cause a negative Q, and we will have an exothermic situation. Okay, so we don't have to worry as much about our signs there because our numbers will work out for us. So we're going to take a look at some examples on how to calculate this, how to use all of these equations, and the different situations we might see. So, part A, first one, we're going to calculate the heat. So we're looking for heat, which is Q, required to change 50 grams of water at 25 degrees Celsius into steam at 120 degrees Celsius. And we've got all of the reference values necessary for this. It says circle the sections or letters of the heating curve this question will cover. So we've got a substance, water, at 50 degrees Celsius, or excuse me, at 25 degrees Celsius. So that is here. So we're going to be in section C to start. And then we are going to heat it to steam at 120 degrees Celsius up here. So we're going to be going to section E. So we are going to heat it up, we're going to boil it, and then heat it again. So that's actually 3 sections of our curve, which means we're going to get a good amount of practice from this question using these equations. Okay, so let's start with part C, or section C. We want to find out how much heat, Q, is gained when we are changing its temperature. So because the temperature is changing during that section, we're going to use Q equals MC delta T. Our mass of our water is 50 grams of water. Our specific heat of water, given here, is 4.18 joules per gram degrees Celsius, which is representing the amount of energy it takes to heat 1 gram by 1 degree Celsius. So if we multiply by grams and then multiply that out, we'll get for 50 grams. And then our change in temperature. For this section alone, we go from 25 to 100 because that's when we hit that boiling point. So that's going to be that first change in temperature. So our delta T is going to be our final temperature, which is 100 degrees Celsius, minus our starting, which is 25 degrees Celsius. Okay? So just for that section, not the whole thing overall. All right, and I'm going to go ahead and calculate that value. So we've got 50 times 4.18 times 100 minus 25. And we get 15,675 joules of energy. So if we look at our units, grams will cancel, Celsius will cancel, and we are left with joules, which measure energy. So that is something I left out up here. Q is going to be measured in joules for both of these. It can also be in kilojoules depending on the situation, especially for our other equation. So this is how much energy it takes just to heat the water to boiling, to get it to start boiling. Now we're going to figure out how much energy does it take to actually boil all the water. So we are taking that, and it's not changing temperature, so we're going to go up here to our other equations. We are vaporizing it, we're boiling it, so it's turning into a gas. So we're going to do our moles times the heat of vaporization. Now we don't have moles, we have 50 grams, but we can change our grams into moles. So, actually I'm going to go ahead and remove that. So we have 50 grams of water. Now we know that we can divide, basically, our substance by its molar mass. So the molar mass of water is 18.02 grams per mole. So we're going to have to just divide that value, and then we're going to multiply it by our heat of vaporization, or enthalpy of vaporization, which is 40.7 kilojoules per mole. All right, if we look at our numbers, we'll have our grams cancel, we'll have our moles cancel, and we are going to be left with kilojoules. So we're going to have 50 divided by 18.02 to get us into our moles, and then we're going to multiply that by 40.7. So 112, let's see, we have 3 significant figures, or I should check my sig figs on the previous one. So 112, which would be 113 if we rounded, 113, and this is in kilojoules. So we can see that these two numbers are in different units right now, and we'll have to deal with that in a second. Let me check my sig figs up here. So we've got 3 in our values, so we're going to round to 3 sig figs. So that 6 would become a 7. Let's go 15, 157, 157, 15,700. There we go. Joules of energy. All right, so we figured out that it takes 15,000 joules of energy to warm up our substance, 113 kilojoules of energy to boil it. And actually, let's go ahead, because we're going to have to add these together eventually. So let's go ahead and change this to kilojoules so that we can compare these numbers. So we divide by 1,000, or move that decimal 3 places. So this is actually 15.7 kilojoules of energy. So if we compare those, heating up the water and changing its temperature doesn't take that much energy. But boiling it and changing it all to gas takes a ton of energy, almost 100 times more, which is amazing. 10 times more, not 100. Wow. All right, so let's check out our last part. Now we've turned it all into a gas, we've boiled it all. Now we're just heating up that gas. So it's still our 50 grams of water. And now we need the specific heat of steam, actually, which I did not include on my paper. So let me get that value, which I believe is in our textbook. Some of these reference values we do have available in our textbook, which it will be on page 132. So steam has a value of 2.01 joules per gram degree Celsius. Okay, so we can see the amount of energy it takes to heat steam is less than it is for liquid water. So now our final temperature that the steam is reaching is 120 degrees Celsius minus its initial, so it started at 100, its boiling point. So we're going to go ahead and calculate that. So 50 times 2.01 times 120 minus 100, and we get 2010. 2010. Now this is again joules of energy. Let's go ahead and change it into kilojoules. Again, move that decimal. So we get 2.01 kilojoules of energy. So again, we can see that it takes a ton of energy to boil the substance and to break all of the intermolecular forces between the water than it does to just loosen them up when we're heating the water, or just heat the steam and make the particles go faster, right? This is steam. The particles are separated from each other. So we're just making them move faster at that point. So if we wanted the total energy it took, we would add these all together. So we have 15.7 plus 113 plus 2.01. We'd have to round to our least number of decimal places, which would be the 113, which would give us no decimal places, so 131 kilojoules of energy total. So this is a more complex problem, obviously. We are heating the substance, we're boiling it, we're heating it again, so we have to do 3 separate calculations there and then add them together to get a total amount of energy. This is not how all of them are, but it's good to use a more complex one so you can see how each equation is used. So when we're changing temperature, we want to use the one with delta T, a change in temperature. When we're not and it's being held constant, then we're going to use our heat of fusion or vaporization, depending on the substance. Now, the other thing to recognize here is I left this value positive, my heat of vaporization, because we're adding energy to boil it. If we were going the other direction and we were condensing the steam into liquid, or if we were in section B and we were freezing water or freezing something, solidifying it, those are going to be times when we have to make that value negative, so we make it exothermic. So this is all endothermic. Okay, we're adding energy. Okay, let's take a look at the next part. So this is part B. So this one, it says a piece of iron metal initially at room temperature of 21.1 degrees Celsius left in a window ledge in the lab on a sunny day. It absorbs 862.4 joules of heat and warms 32.5 degrees Celsius. What is the mass of iron? So we can see from this situation that we are changing the temperature of our iron. We're heating it up. We have the amount of energy it absorbed. We have its specific heat, and we have the mass. So we're going to use the equation Q equals mc delta T. Now it is asking us to find mass. So I'm going to go ahead and divide by C and delta T on both sides. So I have my new equation. So M equals Q over C delta T. and I'm going to plug in. My energy, Q, is 862.4 joules. So I know it's energy because it's in joules. C is our specific heat, which is 0.448 joules per gram degrees Celsius. And then we have our change in temperature. I'm going to go ahead and calculate that. Our final temperature is 32.5 minus our initial 21.1. And we get 11.4. So I'm going to go ahead and multiply by 11.4 degrees Celsius just to simplify my setup here. So you can do that as a side calculation. So if we calculate that out, 862.4 joules of energy divided by 0.448 times 11.4. So I'm putting that part in parentheses to make sure it multiplies before it divides here. So I get 168.85. We only have, let's see, 4, 3, and 3. We have 3 significant figures, so 169. 169. If we look at our units, joules cancel, Celsius cancels, and the grams are being divided. This fraction is being divided, so they're actually, we just end with grams there. So 169 grams of, this is iron, that we are leaving there. So if we take this chunk of iron, set it in the window ledge, if it receives this much energy, it will change this temperature. Have that temperature change. So this is also the type of question we can answer. We can find out how much of a chemical we have based on how much heat it gains and its temperature change, as long as we have that specific heat value. Again, this value shows the amount of energy it takes to heat up 1 gram by 1 degree Celsius. If we compare that back to the one for water from our previous question, where's our water? Our water is 4.18, where this is only 0.448. So water has a very high specific heat, meaning it's really hard to warm it up. It takes a lot of energy to change its temperature. All right, let's check out another one. So we have a 75.75 gram sample of silicon. It's initially at 20.5 degrees Celsius and absorbs 1,326 joules of heat. What is the final temperature of the sample if its specific heat is 0.703? So this one is looking for one of our temperatures. Okay, so my approach to this is, again, we have a change in temperature, so we're going to use Q equals MC delta T. And instead of trying to find my final temperature right now, I'm going to go ahead and just solve for delta T, my change in temperature. So Q over MC gives us our equation. Q over MC. So I'm going to plug into that. So Q is my heat in joules, 1326. I'm going to divide by my mass, 75.75 grams, times its specific heat, which is 0.703 joules per gram degrees Celsius. So if we check out our units, our joules will cancel, our grams will cancel, so we're left with the Celsius, or temperature. And I'm going to go ahead and calculate that. So 1326 divided by 75.75 times 0.703. And we get a change in temperature of 24.9 degrees Celsius. So that is the change in temperature. That is the difference between our starting and our final. Now, we want to know just the final temperature. So we're going to take this one step further. We know that delta T is equal to the final minus the initial. Well, we have our delta T, 24.9 degrees Celsius, equals the final temperature, which we don't know. So I'm just going to put X minus our initial temperature, which is 20.5 degrees Celsius. So I need to add 20.5 to the other side. So our final temperature would equal X. So it would be 24.9 plus 20.5. We would get 45.4 degrees Celsius. Okay, we do that extra step because we are looking for just that final temperature. All right. We got a couple more we're going to try. So again, some different situations. So this says how much energy, so we're looking for Q, is needed to convert 200 grams of solid aluminum into liquid aluminum. Now, we've got a couple clues on what's happening. We've got a heat of fusion, so we're probably going to need to use that. And we have no temperature change. We are melting this substance, so we need to use our Q equals moles times delta H of fusion. Okay, no temperature change. All right, well, we don't have moles, we have grams, but we can take care of that. 200.0 grams of aluminum, and we can go ahead and divide it by its molar mass. Molar mass of aluminum from our periodic table is 26.98 grams per mole. So that gets rid of our grams for us. And then we're going to multiply it by the delta H value, which is 10.9 kilojoules per mole. That allows our moles to cancel, and we can solve. So we have 200 grams divided by 26.98 times 10.9. I get 80.8. We've got 3 significant figures because that's our least amount. So 80.8 kilojoules of energy. So since we are melting this, we're going from solid to liquid. We are adding energy to make that, so we do want this positive value for our answer. All right, last one, how much energy, so Q, is needed to condense 2 moles of oxygen gas? So we've got our heat of vaporization, we're looking for energy. We've already got it in moles, so 2 moles of oxygen times its heat of vaporization. Now here's I'm going to do parentheses here just to make it really obvious. Here's the kicker. We are condensing. We are changing gas into liquid. When we change a gas into a liquid, we are giving off extra energy, right? Heat of vaporization is positive. So if we're condensing it and going the other way, it's going to be negative. So we need negative 6.82 kilojoules per mole. So we are losing 6.82 kilojoules for every mole of oxygen we make into liquid, we condense. So we've got 2 times 6.82, which gives us 13.64, negative 13.64, but we need to round to 2 sig figs, so negative 14 kilojoules of energy. All right. So that is how we can approach these questions. If we solve one of our Q questions, if we were looking for Q and our temperature drops, so we want to watch for that, then your Q value can be negative just like it is here. So if your delta T is negative, your Q is going to be negative, okay? So watch for those as well. You've got some practice questions here, not a ton because we're going to get more practice with this as we go into calorimetry, which is how we actually do the lab technique to measure these values. All right, thanks guys.